Hello and welcome to Lecture 4 of the Traveling Waves unit in Phys 1201. Up to this point in this unit, we've been looking at waves traveling along strings and long springs and things like that, which are essentially one-dimensional situations. But now we're going to look at some two- and three-dimensional situations, and that's going to lead us into power and intensity, which is all about how waves carry energy from place to place. To start thinking about waves in two dimensions, think about a picture like this. So this is an actual picture of ocean waves. Now, most of the time when you see ocean waves, it looks a lot messier than this, but someone got this picture of a day where there were nice, regular, evenly spaced waves coming towards them. And so we can just imagine the view from an airplane where you're looking down and you're seeing these long, straight crests. And they're each separated by the same distance lambda, and they're all traveling this way at a speed v. So this is a snapshot, right? Just like a snapshot graph. And so these lines, which represent crests, would be moving along. And I'm just going to flip them around this way so I can talk about taking a cross section through here, just to make clear that if you take a cross section through here and now look at it from the side, you would be seeing this sort of view of waves that we've been talking about, where each of these lines corresponds to the top of a crest. So we call these lines fronts. And so you can basically think of a front as the line or curve that corresponds to where a crest is when you're no longer in one dimension, but now you're in two, or we'll talk about fronts in three dimensions as well. So if you walk along the front, you're walking along the top of a crest. Now, in the previous example, the fronts were straight lines, but of course they don't have to be. Here's a familiar situation where perhaps a drop has just dripped into this water, and we have these circular waves traveling outwards, and so each of these is what we would call a front. Less familiarly but simpler is if you have some source that's jiggling up and down in the water, so you just keep getting fronts and they just keep coming. And so you get these expanding circles. And so again, our view of this, a drawing of it, shows the fronts now as circles. They're all traveling outward, and they're evenly spaced by lambda again. And remember that this is a snapshot. A moment later, these all would have traveled out a little more, like so, and there would be a new one that's just formed in here at the source, and they would have all moved out. So here's one instant, and here's an instant later. And again, you could take a cross section through all of this and look at these waves from the side. But now you would see that as you move farther away from the source, the waves are not as tall. And you can understand this in terms of energy, because if you think, say, of this crest, well, right at the crest, all of that water has gravitational potential energy. And that gravitational potential energy came from the source, right? The source wiggled here, and it set the water in motion, and the energy associated with that has now been carried out by this wave crest. And so the height of the crest is connected to how much energy each little bit of water has. And it has to be conserved. So when this crest travels out farther, say to here, it has the same amount of energy that it had here, but that's now spread out through more water. So that same amount of energy is being shared with a larger quantity of water. And so the crest will not be as high because each little bit of water has less gravitational potential energy in here than the bits of water did in here when this crest passed them. So we can extend those same ideas to 3 dimensions, although they start to get a little harder to picture. So in 2 dimensions, when we had a source at some point, it produced circular waves. Now, in 3 dimensions, unlike this case where the waves travel out on a surface, in 3 dimensions, like a light bulb or a speaker or something like that, the waves are now traveling out in all directions. And so instead of circles, you wind up with spheres. The wave fronts, instead of being circles, are now spheres. Now, one thing that's important to realize is that far away from, say, this 2-dimensional source, if you go far enough away, those are bigger and bigger circles, and if you're standing on one of those circles, it won't seem so curved if you're very far away from it, because these are now big circles. And so far away, the circular waves look like straight line fronts. Well, similarly, when you're in 3 dimensions and you're far away from a source, those spherical waves now look like planes. Just like when you're standing on the surface of the Earth, you don't notice that you're standing on a sphere. It looks more like you're standing on a plane. If you're far away from this source, so that the spheres that are its fronts are very big, they will seem like planes. And note, this picture can be a little misleading. It's not that if you are sitting here as this plane approaches you, you would be picked up here. No, this is a function describing perhaps an electric field vector or something. And this is saying that everywhere on this plane, it has a large magnitude, whereas here it has a small magnitude. Everywhere in a plane out a little in front of this gray one and out a little farther, it's big again but pointing the other way. So I realize that's probably hard to picture. Plane waves are a little difficult to get your head around at first. Now we're ready to talk about intensity. And you can think of what is probably a fairly familiar idea. Here we have sunlight. Okay, and so the sunlight is all coming down like this. And it's the same brightness everywhere. And the brightness is a good way of thinking about what intensity means. We have a small solar panel and a large solar panel. And let's say other than their sizes, they're otherwise basically the same. Then which one is going to give you more power? Well, I think you know that the large solar panel is going to, although you may not have thought about why. At a very basic level, you could just say it's catching more light, and that's basically true. The sunlight is carrying energy. So per unit time, a certain amount of energy arrives in any little area that you look at. And if the sunlight is the same brightness everywhere, then the same amount of energy per unit area arrives everywhere each second. And so that's why the large solar panel collects more energy, because it's catching more of the light and the light is carrying a certain amount of energy per unit area. So this idea then gives us this idea of intensity, which is the power delivered, so that's energy per unit time, per unit area. And we'll write that I is P for power over A for area. A particularly useful thing with intensity that comes up often is how the intensity falls off for spherical waves. We talked vaguely about with circular waves how the amount of energy per unit, say, length on the circular wave decreases. And so this is why the wave height gets smaller for circular water waves. There's a similar thing that goes on for for spherical waves. And because it so commonly comes up, for examples in discussion of lighting and use of speakers and things like that, it's worthwhile to know it. So let's say we have a source here, and this could be any source of waves that's spherical. So it could be a light, it could be a speaker. So this is either light propagating out, or it could be sound propagating out from the speaker. And let's say this source is putting out waves with a particular power, right? So you're probably used to thinking about perhaps speakers having a power associated with them. And so let's just say, for sake of argument, that the power of our source was, I don't know, typical speakers, 100 watts is pretty reasonable. And now here we are at some distance r1. And I'm going to say, why don't we make r1, I don't know, 2 meters. We're a little bit across the room from our speaker. So that tells us we can right away calculate the intensity, because however much power the speaker is emitting, on this front, that power is spread evenly over the area of this whole spherical front. And so we can say I1, right? So that's going to be the intensity on this front is just the power divided by how much area it's spread out over, right? So that's going to be 4 pi times this radius squared, right? That's the area of a sphere, and that's easy enough to work out, right? 100 over, that's basically 12 times 4, 4,800. 12 over, it's very close to 2 point mumble watts per square meter, right? 100 divided by something very close to 50. And now if we walk across the room so that instead of being 2 meters from the speaker, we are now, let's say, 4 meters from the speaker, then we see, so now that same amount of power is spread out over this larger spherical front. And so I2, the intensity at that distance from the speaker, is going to be 100 watts over 4 pi, 4 meters squared. Note, that's going to be 1/4 of what we found here, or about 0.5 watts per square meter. And so this is what is referred to as a 1 over r squared drop-off, right? We have in general here that our intensity at distance r from our source is the power of our source divided by the area of the sphere that we are on, like so. And so that's a constant usually. You could turn up the volume and change it, right? But if you're not doing anything like that, then this is a constant. And so the intensity just decreases as 1 over r squared as you go farther away from the source.